or 3 feet wet and also review, because everything we're going to talk about today is review. Okay. May not be very fresh in your mind, but you have learned it all. So chapter 4, section 3 is called right triangle trig. So all the stuff we did with the unit circle, finding the sine, the cosine, the tangent of angles, you can use the unit circle to find, but you can also use your right triangle trig. There are other things that are just right triangle trig in which you couldn't use your unit circle. So that's what the focus of today is going to be. And Monday. So SOHCAHTOA is a word you need to know how to spell. This is like one of those words, like if you go home and you ask your parents, like, do you remember SOHCAHTOA? They'll be like, maybe. They maybe couldn't spell it for you anymore, but they probably remember that word. And it is an acronym for sine, cosine, tangent. So sine is the opposite, which is what O stands for. So opposite over hypotenuse. Cosine is this AH, adjacent, over hypotenuse. And the tangent is the TOA part. Tangent equals opposite over adjacent. So if you can spell SOHCAHTOA, you should be able to figure out your trig functions. Now think about how we could add in our reciprocal functions, right? So sine would lead to cosecant, and cosecant would be hypotenuse over opposite. Cosine would lead to secant, so secant would be hypotenuse over adjacent, and cotangent, or tangent would lead to cotangent, which would be adjacent over opposite. So now, obviously, in geometry, you did like word problems and that kind of stuff, which we'll do a little bit of, but most of those you could solve using sine, cosine, and tangent. If I give you something that just asks for a specific angle, those trig functions could also include cosecant, secant, and cotangent. The other thing you've got to remember is, let's do this. So if this is on the left is my right triangle, we'll talk about the circle in a second, but on the left is the right triangle. So if I am going to label a triangle, and we don't do a ton in this, but we will come back to it. When we do law of sines and law of cosines, you have to label them. And your vertices are A, B, and C, then the lowercase version of that letter is opposite it. So A would go opposite A. And so if I asked you for the sine of theta, what would the ratio be? A over C, good. And the cosine of theta would be B over C, and the tangent of theta would be A over B. And then cosecant, we would literally flip the sine. Secant, we would flip the cosine, and cotangent, we would flip the tangent. So now what happens with the overlap is that if I take that triangle and I put it in my unit circle, it would look something like this. So this is my radius, right? That radius has a value of 1 if this is a unit circle. And so the x is if my theta is here, the x is the adjacent side, right? And the y is the opposite side. So it should make sense that your sine is your y over your 1, because it would be y opposite over hypotenuse. That's the overlap, okay? The cosine would be the adjacent, and the adjacent would be the x. So that's where the coordinates get assigned their trig functions. And then if it's a special right triangle like 30, 60, 90, 45, 45, 90 triangle, we actually know those values. And that's where we get the coordinate points on the unit circle. So this, I honestly won't focus too much on this, but all this slide means is that you can have a teeny tiny 30, 60, 90 triangle, and you could have a big, huge, the size of a building, 30, 60, 90 triangle, and the ratio of the sides will always be the same. If you remember from geometry, these are similar triangles, and similar triangles always have the same angle measurements, right? And their sides are proportional. So if I have a teeny tiny 30, 60, 90, I can figure out the lengths of my sides and get a ratio, and also it would be the same for a huge one. So the sine of a teeny tiny 30, 60, 90 triangle is the same as the sine of a big, huge 30, 60, 90 triangle. Same for cosine, same for tangent, whatever, for any triangle. All right, so we start with Pythagorean theorem, okay? This says find the value of each of the 6 trig functions of theta given b is 4 and c is 2 root 5. So I labeled those 2 sides. But in order to find all 6 trig functions, you need all the sides, right? So, and we're missing a, and this is where our a squared plus b squared equals c squared comes back into play. It doesn't matter what A and B are as long as C is the longest side or the side opposite the right angle, right? So in this triangle, I could make 4 squared plus, or A squared plus 4 squared, if I go in the right order, equals 2 square root 5. squared. So then a squared plus 16 equals 2 squared, which is 4, and square root of 5 squared, which is 5. A squared plus 16 equals 20. A squared equals 20. Nope, a squared equals 4. And a equals. Now, technically, this answer is plus and minus 4, but a side length can never be negative. So that is a 2. A side length of a triangle, not inside the circle, but any. So now my sine of theta, theta's in this corner, sine of theta would be 2 over 2 root 5. And that gets simplified to 1 over root 5, and that gets rationalized to root 5 over 5. The cosine of theta is 4 over 2 root 5, which becomes 2 over root 5, which becomes 2 root 5 over 5. And the tangent of theta is opposite over adjacent, so 2 over 4, which is 1/2. We good so far? Yeah. Now, when I find the reciprocal functions, my advice is if you have rationalized, go back to before you rationalize. So when I want to find the cosecant, I don't want to come to the end and flip root 5 over 5. I'm going to re-rationalize something I already rationalized. Instead, I go to before I rationalize. So I would come to the part that is 1 over root 5 and flip it from there. And I just get root 5. And then the secant of theta, I would go back to before I rationalize the cosine, and I get square root of 5 over 2. And then the tan of theta, I'd get 2. I mean cotan, sorry. Cotan of theta. Questions on those? Okay, last thing we'll review is, again, this is from geometry. It was in Algebra 2. This is a standardized test, like something they love to ask about. And that is the ratio of the side lengths of 2 special triangles. A 45-45-90 triangle and a 30-60-90 triangle. So every single 45-45 and every single 30-60-90's ratio of their sides are the same. In general, any 45-45-90 triangle, we would say the side opposite the 90 gets 2, no, sorry, the side opposite the 45s are A and A, and the side opposite the 90 would be A root 2. So this is if it's a 45-45-90 triangle, which would be an isosceles right triangle. And then any 30-60-90 triangle, the ratio of the side lengths are opposite the 30 is the A, opposite the 60 is A root 3, and opposite the 90 is 2A. And those values, that A could be 1, that A could be 10, that A could be 3, whatever it is, those are always the ratio of the sides. So in a question like those, they will give you one of the 3 sides. You would figure out which side length you're given by like what of the part of the ratio it is, which if it's the A or the A root 2, like that kind of, and then you would solve for the remaining sides. But as soon as you put that triangle, as soon as you make A1 on it, which is what happens when we put it in the unit circle, those A's become 1s, and the root 2A would also become just root 2. And if you put it inside the circle and you make the A1 on a 30-60-90, then opposite the 30 is 1, opposite the 90 is 2, and opposite the 60 is root 3. And that is how you can find the sine of 30 degrees, the sine of 45 degrees, the sine of 60 degrees, the cosine, like all the same things that we find using the unit circle, you can use using your triangles. So in these examples, we're going to use triangles. You could also use unit circle. Like when it comes time for the test and it asks you to find the sine of 30 degrees, you could use the triangle or you could use the circle. I don't care. But since we're in this triangle section, we're going to use the triangle. So if I want to find anything of the 30 degrees, I'm going to draw out my right triangle, 30, 60, 90. I go opposite the 30 is 1, opposite the 60 is root 3, and opposite the 90 is 2. So those side lengths you have to know. And now I can find the cosecant is the reciprocal of sine, and sine is opposite over hypotenuse, so this is hypotenuse over opposite. Secant is the reciprocal of cosine. Cosine is adjacent over hypotenuse, so this is hypotenuse over adjacent. And cotangent is the reciprocal of tangent, opposite over adjacent, which means adjacent over opposite. And 30, we put in the corner on the bottom left. You can put anywhere you want, but opposite it should always go to 1. So cosecant of 30 would be 2 over 1, which is 2. Secant of 30 would be 2 over square root 3, which gets rationalized to 2 root 3 over 3. And the cotangent of 30 would be adjacent over opposite, which is root 3. And then cosecant of 60, secant of 60, and cotangent of 60. Now we're focusing on 60 degrees. So opposite, this is still the same thing, hypotenuse over opposite. This would be hypotenuse over adjacent, and this would be adjacent over opposite. So the hypotenuse is 2. The opposite side of 60 is root 3. That gets rationalized. The hypotenuse is 2. Adjacent to 60 is 1. So this becomes 2. And the cotangent, adjacent over opposite. Adjacent is 1. Opposite is root 3. And that gets rationalized. So again, it is completely up to you by the time we get to the test. Like, it is completely up to you if you want to say, okay, I know 30 degrees is my over 6 and my over 6 is this coordinate point. Or if you want to use your right triangle. Yeah. So usually, I'll probably do the same thing. Usually if it's a test in which it fills the time, like I'm not worried about, like timing is of the essence, I would say, then I will give you a small blank unit circle the day before the test and give you 5 minutes to fill it out. And then you'll get that back the next day. Does that make sense? So at least